finally ready to talk about momentum. Let's just jump right into it. So, what is momentum? In order to talk about momentum, we first have to distinguish between velocity and speed. So, let's talk about velocity. Velocity v, it's almost always written as v with a little hat. Lowercase v with a little hat, you should always assume to mean velocity. The velocity vector consists of two parts, vx and vy. It has units of meters per second. It refers to, a speed, basically. A speed, but I know whether it's going to positive x or negative x, positive y or negative y, and how much in each of those directions. So speed is the magnitude of v. So speed is vx squared plus vy squared square rooted. So this is a scalar. It's just a number. And the velocity is the vector. Momentum is velocity scaled by mass. Velocity scaled by mass. So the way that we write momentum is with a lowercase p with a hat. So momentum is mass times velocity. So when I talk about the momentum of an object, usually I talk about like just an object with some mass moving along at some speed v. I say that this thing has momentum p hat that points. It's going to point in the same direction as velocity. So p hat always points in the same direction as velocity. Why? Well, again, if it's just velocity being scaled by mass. Mass is always positive. So in terms of that stretching and compressing of a vector that happens when you multiply it by a scalar, mass can only stretch or compress it. It's not going to do anything to change its direction. So momentum always points in the same direction as velocity. The units of momentum, units of p, are just mass times velocity, right? So it's going to be kilogram times meter per second. So that's the base SI unit of momentum. So the reason that physicists care about momentum is because it turns out that momentum is one of those conserved quantities. The total momentum of a system over time, as long as there's no outside forces acting on the system, the total momentum is conserved. So if you looked at the whole universe and you said, what's the momentum of the universe? That number is a constant. If you have a system, so again, any system that's not being affected by outside forces, then that system's momentum is constant in time. It's conserved. Okay, so we write that a couple of ways. So we say that, again, if there are no external forces, this is called momentum conservation. If there are no external forces on my system, then the initial momentum is equal to the final momentum for my system. So if my system is composed of many little parts, like a bunch of different little blocks moving around, a bunch of little different masses moving around, then one way that I can rewrite this is by thinking about the total momentum as the sum of individual momentums of the particles. So each of these particles are little masses. I'll call mass 1, mass 2, mass 3, etc. And each of them has a corresponding velocity, which is a bunch of their own little individual velocity vectors. So the way that I can write this statement in maybe a little bit more of an explicit, useful way is to say that the sum of all of the individual momentas, the initial velocities times the initial masses, is equal to the finals of those things. Okay, and usually we won't treat the masses of objects as changing. So for the most part, you can just kind of neglect the subscript I, subscript F, or subscript I and subscript F on the masses. Okay, so each of these sums is called the total momentum of a system. So if I have a system that's composed of multiple parts, the total momentum is just the sum of all of the individual momentas, all of the individual momentum. The way that I think about momentum is it tells me something about how the center of mass of a system is moving. So if I know that, say I've got like this collection of particles, and I know that the total momentum is like pointing to the right, that tells me that the center of mass of all these particles is pointing to the right. Over time, I expect that the average of these particles moves rightward. That's all that total momentum tells me about. So say that I had one mass that was 3 kilograms, and it's moving up at a speed of 2 meters per second. And I've got a second mass that is 4 kilograms. Ooh, that's a little too thin. Hang on. That is 4 kilograms, and it's moving to the right at 8 meters per second. And this is my system. I'll draw a little bubble around it, say this is my system. The total momentum of the system, momentum total, is, so for the first one, it's going to be 3 kilograms and 2 meters per second. That's going to be my y component. For the second one, it's 4 kilograms and 8 meters per second. So to break it into parts here, that's px and py. So I think now about each of the individual momenta. So this box would have a momentum vector that looks like, I'll call this P2. This will be my second one, this will be my first one. P2 would look like, so the x component for this is going to be 4 times 8. That's mass times velocity. And the y component, since there's no component of the velocity in the y direction, is just going to be 0. So 4 times 0 makes 0. For this first box, momentum 1, well, what's that going to be? It's going to be 3 kilograms times 2 meters per second, and there's only a vertical component. So since my horizontal component to the velocity is 0, it's 3 times 0. The y component, the vertical component, is going to be all of that 3 times 2, so 6. So 3 times 2 makes 6. So what do I get? I get 32, 0 kilogram meter per second and 0,6 kilogram meters per second. So the total momentum of this system is just the sum of those two things. It's going to be, let's color code this. It's going to be 0, 6 plus 32, 0. And the total is going to be just 32,6. So this total momentum for my system, as long as there's no external forces acting on my system, it will maintain this momentum throughout time. These two numbers will stay the same forever. Okay, it tells me roughly that the center of mass is moving to the right and up. So 32,6 is going to give me a vector that looks kind of like that. It's mostly to the right and a little bit up. It's telling me that the center of mass is moving to the right and a little bit up. All right, that's all I really wanted to talk about for momentum right off the bat. Up next, we'll talk about forces and impulse, the mediators of change in momentum. So how does momentum change in the presence of forces? And we'll play a little bit with a 7B specific construct, which is the momentum diagram. I also wanted to leave you with Newton's first law. Newton's law says an object moves at a constant speed along a straight line unless acted on by a net external force, which is to say that momentum is conserved. That's pretty much all he's saying. The last three rules will make sense in a second. We haven't yet talked properly about forces, although I know you've seen it in 7A. Cool. See you in the next one.